So today's topic is about the Ohm's law and how we can relate the resistance of different materials by the IV graphs. So according to Ohm's law, voltage is directly proportional to current, or a current in the which is passing through a wire is directly proportional to voltage across the component. So V is directly proportional to I. Whenever we replace the proportionality sign, we always replace with equal to and a constant. So V is equals to Ri, or we can also say V equals I R. So this is a formula which relate the voltage and a current. So what is the resistance? Simply we can say that the resistance is actually a ratio between the voltage and the current. How we can find the voltage across the component? So for that we use a voltmeter. Voltmeter is a device which is used to measure the voltage across the component. And I is a current. So for measuring a current, we use an ammeter, which is connected in series, where voltmeter is connected in parallel. Now, when we sketch a graph for different components, the current and voltage graph, which we also call IV graphs. So for IV graph, it can be four different components. We can sketch a graph. Current is on y-axis and the voltage is on x-axis. Or it can be other way around, and the shape of the graph will be different. So if we have current on y-axis and we have a voltage on x-axis, here we have also current on y-axis and the voltage on x-axis. The current is on y-axis and voltage on x-axis. Here as well, current on y-axis and the voltage on x-axis. Now, from this graph, because we have the formula V equals IR, so the resistance is actually a ratio between voltage and current. R is equals to V over I. As we take the slope or the gradient of the graph is a quantity on y-axis divided by quantity on x-axis. So on y-axis we have current, on x-axis we have voltage. So in this case, when we have a current on y-axis and the voltage on x-axis, the slope is always reciprocal of the resistance. Means the slope of this graph will always be equals to 1 over r. Now, if we have an ideal conductor, a conductor which is or a fixed resistor. So for an ideal conductor or a fixed resistor, we assume the temperature is not changing, so it won't affect the resistance. So we'll always have a straight line. And if we want to find the resistance from this graph, we'll take a slope and take a reciprocal of the slope. We'll get the resistance because resistance is 1 over, as the slope is 1 over r, so r is 1 over the slope, the inverse of the slope. This is for ideal conductor. But if we have a filament lamp, so initially, because when we increase the voltage, the current will also increase. But as the filament get hot, the increase in temperature, increases the resistance, and we know slope and resistance are inversely proportional for the filament. So if the resistance increase, the slope will decrease. So the gradient or the slope of this graph will decrease. This is for the filament. But if you have a thermistor which is a heat resistor, initially the resistance of a thermistor will be high, but as the temperature increases, the resistance of the thermistor decreases. So here the slope is reciprocal of the resistance. So as the increase in temperature reduce the resistance, as the resistance decrease, the slope will increase. So this will get steeper. And the last one is a diode. When we sketch a graph for a diode, we observe this shape. That is what we observe. Initially, the diode is having infinite resistance, and then the resistance of a diode, it's because as the slope is increasing, it means the resistance is decreasing. But why for a diode the graph is like this? That is what is the topic today. That why the explaining the shape of the graph, the IV graph for a diode, and then we'll do the potential divider circuit. For to understand the concept of a diode, the shape, you have to understand the internal structure of a diode. And for understanding the internal structure of the diode, you have to understand the concept of a semiconductor. So, what are semiconductors? The semiconductors are actually the group 4 elements are semiconductors. Let's take example of the silicon. Silicon, germanium, these are semiconductors. So, the structure of a silicon, it is a giant covalent structure, and there are 4 covalent bonds silicon is formed with another silicon. Now, what will happen because of the heat or the light, when there is a heat energy or there is a light energy, what will happen? One of the electron out of 1 million, like if we have 1 million atoms or group of atoms, then as a result, out of 1 million, only one electron will move out. When this electron will move out, there is a vacancy of the electron, and that vacancy of electron, what we call that as a hole. So, due to heat or a light, it produces electron and holes. And these electrons move within the structure. That's why the semiconductor allow the electricity to pass through. Vacancy of electron means like electron should be there, but it is not there. Like it's not present. This electron, because of the energy, it is coming out. And this electron, when it come out, the structure does not break down, only the bond break down. So in a semiconductor, what will happen? Yes, I will repeat. Group 4 elements. You have silicon. Silicon is forming 4 bond with another silicon. So 4 covalent bonds are there. So because of the heat and the light energy, one of the electron which is involved in the bonding, like say this electron is there involved in the bonding, will jump out from the bonding. When this electron will move out, what will happen? There is a space available for electron to stop. This space which is available for electron to stop, what we call that as a hole. So because of the light or the heat energy, both are the forms of energies. So because of the heat or the light, the electron and the hole pair is created. This is what initially happened. So when the light or heat energy, it causes the electrons to be removed from the structure. When electron removed from the structure, so if the electron leave the space, what we call the place which is vacant now, that is we call that as a hole. So it create an electron or hole pair. And these type of semiconductors, we call them as intrinsic semiconductors. So intrinsic semiconductor, the electron and the hole pair are generated, and the number of the electron will always be equals to number of the holes. Because if one electron move out from the structure, it means one hole is created. If two electrons move out, two holes are created. But this happened for a very few, like out of 1 million, it happened for 1 or 2 atoms. So it's a very low percentage. So intrinsic semiconductors, yes, they do conduct, but they conduct a very small amount of current. Then how we can increase the conduction? To increase the conduction, we do a process we call doping. So we dope a semiconductor. We dope a semiconductor. What is the meaning of term doping here? Doping means we add impurities. Impurity means like we add element from group 5 or like another element is added, we call that as impurity. So we dope a semiconductor, and the semiconductor which is doped, is known as extrinsic semiconductor. And what happened? It can be doped by two ways. Either we can dope by adding a group 3 element, or we can add a group 5 element. If we add a group 3 element, like example, say group 3 element, we have boron. Already the structure is there. Like this is a original structure of a semiconductor, which is having silicon bonded with four other silicon in a giant structure. This is already there. What we did now, we add a group 3 or a group 5 element. Now, if we add a group 3 element, let's say we add boron. So boron is a group 3 element. So how many electrons the boron is having? It is having 3 electrons. So 1, 2, and 3. So what will happen? One silicon will form a bond here. Like what is the concept of a doping? We remove silicon atom. One of the silicon atom is removed from the structure, and like let's say this silicon atom. So we remove this silicon atom and we add boron. So when we add a boron, so as a result, what will happen? So this silicon will form a bond here with boron. This silicon will also form a bond with boron. This silicon will form a bond with boron. But what about this silicon? As boron does not have any electron available, so this silicon is not able to form a bond. So there is a vacancy of electron, and what we call this vacancy of electron, we call that as a hole. So when we add a group 3 element, like it's not like all silicon atoms are removed and we add all three group 3 element. It's like we remove a proportion of a silicon atoms and we add a boron. So as a result, boron will form three covalent bond with other silicon, but one still is available, but it's not able to form a bond as it does not have an electron. So there's a vacancy of electron is created, like there's a space for electron to stop. So there's a space for the electron to stop here. So what will happen when we add a group 3 element? What we call in this case, we'll have more. So there are, if you compare like when it is the semiconductor, intrinsic semiconductor, the number of the electrons will be equals to number of holes here. And here also number of electrons is equals to number of holes. There are electron and holes already there. But when we add a group 3, as a result of adding a group 3 element, what will happen? There will be more holes because electron is not here. So if we compare, so when group 3 element is added, the number of the holes will be greater than the number of electrons. So there will be more holes than compared to the number of electron. So these type of semiconductors, we call them as a p-type semiconductor. So this is called a p-type semiconductor. So in a p-type semiconductor, we add a group 3 element. When we add a group 3 element, like group 3 element forming a 3 bonds, but still one is available, like it does not have electron to form a bond with another silicon. So there's a vacancy, a space is there that electron can stop here. So that's why we call that as a hole. So in a p-type semiconductors, we have majority of the holes and we have few electrons. Is it clear till this point? But what happened in when we add a group 5 element, when a group 5 element is added, say we are adding arsenic or phosphorus, removing silicon and adding arsenic. Like in this silicon is removed and we form arsenic is added. So this silicon will form a bond, this silicon will also form a bond, this silicon will also form a bond, and this silicon will also form a bond. But because arsenic is a group 5 element, so one of the electron is free now and this electron will go out. So when this electron will go out, These type of semiconductors, they will have more electrons. The number of electrons are greater than the number of the holes. And what we call these types of semiconductor, we call them as N-type semiconductor. N-type means negative type semiconductor, because you can see majority of them are holes. Majority of them are electrons. There are holes as well. From where we get the holes? Because already, like in the semiconductor, electron and holes are already there. But when we add arsenic, we increases the number of electrons as compared to that of holes. Holes remain the same number. Like, let's say when it was not doped, it was having just 10 electrons and 10 holes. But when we do carry out a doping, like adding a group 5 element here, so the number of electron will be more and the holes will remain same. Holes and electron are always there in a semiconductor. So as a result, what will happen? This type of a semiconductor is known as N-type semiconductor. So semiconductors have electron and holes. When we add a group 3 element, it will have majority holes than electrons. If it is a group 5 element is added, it will have majority electrons than holes. So both ways we are increasing a conduction. One is known as a p-type semiconductor, another one is known as n-type semiconductor. Is it clear till this point? The concept of intrinsic and extrinsic semiconductors? Any doubt in this? No, this is extrinsic. In extrinsic semiconductors, we add impurities, but intrinsic, like this was intrinsic. When impurity was not added, it was intrinsic. But when impurities are added, that is extrinsic semiconductor. And extrinsic semiconductors are either N-type or P-type.